Welcome everybody to today's Meshwork webinar. Today we're fortunate enough to have Toby Maclean coming to talk to us about the challenges of balancing embodied carbon against the certainly well-established approach of trying to reduce operational carbon in buildings. But I'm far from an expert on this, and hoping that Toby is at least more of an expert than I am, but I imagine very knowledgeable. So I'm going to hand over to you, Toby, and let you make a start. Just before we kick off, we want to make this a really open discussion if we can. So we'd encourage you to type any questions into the chat as they occur to you. And Toby has pointed out, and I know because I've seen the presentation, there are one or two quite technical slides that certainly I had questions on when we ran through it the other day. So if you have questions relevant to a particular slide, please do put your hand up and or come off mute and ask your question directly so that Toby can respond to it. And if you have the question, it's highly probable a number of other people have the question and are probably not quite as bold as you are in asking it. So I would encourage you to do that. And then we'll have hopefully some time at the end to have more of a discussion and or any generic questions that we might want to ask. So thank you very much, Toby, and I shall hand over to you.
Thank you, Simon. And hello, everyone. I'm Toby Maclean. I'm a structural engineer by training and trade. And I established Allt Environmental about 4 years ago with the stated aim to try and work out how to decarbonise the built environment. And I guess I'm still working on the answer to that. When seeking to minimise operational carbon emission or energy use. And the versus in this title, embodied carbon versus operational carbon, sets the two types of emissions in opposition, and there is certainly some tension between them. But the atmosphere and hence climate impacts make no distinction about where the carbon dioxide swirling out has come from. So it simply matters that the sum of those two, embodied and operational, is as low as possible, assuming we ignore some temporal effects, which we'll talk about later, perhaps. And so what drives the attention on embodied carbon? It's not the national government, although there are starting to be murmurings there. There are calls from designers, industry, enlightened clients to reduce embodied carbon, and no doubt for many here, it's a key driver in design, but it's, and when I say many here, I mean many on this call, but it's not a mainstream approach still. And in my recent experience, when people talk about net zero buildings, about 80% of the time they're talking only about operational emissions. And about 20% of the time, they're probably under the misguided understanding that it's possible to have a net zero building that includes embodied carbon. And it's not currently. So in terms of operational carbon, it's since the mid-1980s, successive editions of the building regulations have attempted to reduce the operational energy that buildings use, and hence their operational carbon emissions. And Part L of the English and Welsh building regs is the most frequently updated part of the building regulations. And it is and was a very sensible thing to do. And as over time, operational emissions for a building can quickly outstrip the embodied emissions for a building. And it's a good case to say that we should have tightest energy efficiency regulations still. But it is at odds with the regulation of embodied carbon in the UK. There's some good news. It's not just legislation-driven and virtue-driven design improvements that are reducing operational carbon. The increasingly common switch to electric heating and hot water, the boiler ban for 2025, which at time of writing is not a boiler ban, but is a target to have 80% less boilers by 2035, will help, obviously. And And so all that means is reliance on electricity as opposed to fossil fuels means as the grid decarbonises, so do operational carbon emissions. And the graph here are the projections, slightly out of date because the latest one was released this week from the National Grid, and these are future energy scenarios. And they predict how the grid may decarbonise according to certain routes and assumptions over the next 30 years or so. And there are a range of assumptions here, from falling short, which is the red dashed line at the top, to leading the way, which is a kind of grey dashed line towards the bottom. And the EEP 2021, the blue dashed line, which starts quite well and then doesn't perform so well for later years, are the BEIS predictions. So operational emissions are going to reduce with the grid, regardless if we do nothing. And what it means is, if you consider that an embodied carbon emission as an investment that will produce operational carbon returns, then those operational returns will be diminishing over time. So if you don't make your return on that investment quickly, you may never do. Now, I've got to warn you, there are a lot of graphs in this presentation, so do prepare yourself. This is just the first of many. And as Simon said, please do, if there's a graph you don't understand after my explanation, please do clarify what I mean. But the grid decarbonisation is going to be good for embodied carbon too, taking a random product, so insulation product. As the grid decarbonises, so will the embodied carbon in most UK manufactured things, with some outliers like metals and cement that currently need fossil fuels to reach their temperatures needed for manufacture, and in the carbon dioxide release from things like calcination in making cement. That's when limestone is burnt and CO2 is released directly to atmosphere. So in this case, this insulation product, looking at the EPD for it, we see that it had quite a lot of non-renewable energy used in its manufacture. And if we assume a certain grid intensity at that time, we can work out more or less, this is a very, very, very approximate calculation, but it gives you the idea. We can work out more or less what the carbon dioxide emissions were for that energy use. And therefore, and it turns out it's about 6%. And so therefore, if we halve the grid intensity, we'd result in a reduction of about 30% of the embodied carbon of this product. So that's the good news. It's not quite as fast as a direct proportional relationship, but it does mean we're on the right track in terms of embodied carbon, even as operational emissions go down. But there is still this question about when is doing too much of a good thing, too much of trying to reduce your operational emissions, and this is the main thrust of this talk today, actually going to give you an overall carbon benefit, or potentially result in emitting more carbon than doing a bit less of that thing in the first place. And so it's the balance between embodied and operational emissions. So this slide shows that adding insulation to a building can increase the embodied carbon to a point that the extra embodied carbon for the extra insulation is never compensated for by the reduced operational carbon that extra insulation has achieved. And these graphs are based on each a certain prediction for the grid. In this case, it's the falling short prediction, i.e. the most pessimistic prediction for the grid. And it's for some insulation, in this case polystyrene, all the numbers from EPDs. It assumes a certain climate, in this case 2,400 degree days, heat degree days at 15.5 degrees Celsius. And a slightly surprising thing is that we find that the least carbon solution over the lifetime, or certainly over 30 years and therefore the lifetime of the insulation, produces a U value that wouldn't be accepted by building regulations, Part L. So the graphs on this curve are different thicknesses of insulation. The blue one at the top, which goes up very high, is virtually no insulation, just the wall makeup. It's modelled as a U value of 2 at that point. What might be a typical uninsulated wall in many buildings. And then the other colour lines on this graph represent different thicknesses of insulation in 30mm increments. So from 30mm insulation to 240mm insulation. And of course, as you add more insulation, you add the embodied carbon, which is why on the y-axis, each graph starts progressively higher up that axis. And the higher up the axis it starts, you'll see there's a smaller change between the start of the x-axis and the end of the x-axis after 30 years, because you've got lower operational emissions. So looking at the orange line, that's 30mm insulation. The first thing to note is it's a massive reduction in energy use compared to no insulation. Even a tiny amount of insulation is a great thing to do. But you'll see that adding a bit more insulation helps over the 30 years in terms of carbon emissions. But the absolute lowest one, the one that produces that 23.2 at the end, represents 120 mil of insulation, a U value of 0.24. And there's some caveats on this. The graph is just for a square meter of wall. It assumes all thermal bridging and airtightness is the same regardless of installations. And perhaps, importantly, for very low level of insulation, it assumes the heating kit does not increase in size to compensate for additional heat losses. But it also ignores any additional structure you might need to support thicker layers of insulation. And also the extra envelope you need to cover those additional thicknesses of insulation. So that's one extreme in a way. So we've got a pessimistic grid. We've got a heat supplied by a heat pump. So it's assuming a coefficient of performance of 3. But if we were to look at an alternative, which is a very low carbon insulation, in this case, blown cellulose, so recycled newspaper. But again, with the heat pump and the pessimistic prediction for the grid, the graphs are very similar. The blue one is the uninsulated building, and then different thicknesses of the cellulose insulation in increments of 100 millimeters this time. We find that the lowest carbon by a little bit is 400 millimeters of insulation, a very low U value of 0.08, and we probably wouldn't go that low for other reasons. So just for the avoidance of doubt, this is not an argument to say we should poorly insulate buildings. We should insulate our buildings well. But it is a note to say we should think about how we're insulating our buildings and what we're using and what level we're insulating to.
Toby, can I just ask a question? You've talked about this in the previous graph being based on, if you like, the worst case predicted for our grid and the operational energy that's being supplied to the building. What impact would there be if we went to the best case scenario for the national grid?
So the more the grid decarbonises, or the faster and more it decarbonises, the bigger this effect, i.e. in carbon terms only, the optimum amount of insulation will reduce. So if we were to run this with the ambitious decarbonisation projections, the optimum U value for carbon only considerations would be higher than shown here.
Yeah.
A worse U value.
Interesting. Thank you.
And of course, carbon isn't everything. Reducing energy use is important, both to enable more rapid decarbonization of the grid and for lower bills for consumers. And better insulation makes more comfortable homes. But the takeaway is it is possible to get a very well insulated home and also have an optimum carbon result, as this graph shows. Briefly touching on another popular question, which is triple glazing or double glazing. And it's quite easy to show a range of results when considering the carbon of triple glazing against double glazing. But it is highly dependent on how the grid decarbonizes and how the heating is provided, basically whether there's a heat pump or not. And the climate, obviously, in a cold place, triple glazing is much more likely to be worthwhile in carbon terms than in a warmer place. But for example, with a pessimistic grid assumption and no heat pump, the carbon payback of triple glazing could be around 4 years. Again, it all depends on which glazing manufacturer you look at and their EPDs and so forth. But with an optimistic, and that's the left-hand graph, but with an optimistic grid assumption and with a heat pump, you may never get carbon payback on your triple glazing. And a graph that's not here is a heat pump combined with a pessimistic grid decarbonisation, and then the payback might be around 12 years. So 12 years is quite a long time. It's pretty worth doing, but it's quite a long time to wait for your carbon payback when we're in a climate emergency. And again, there are other reasons why you might want to have triple glazing, for example, comfort for the users. And these graphs are really talking only about the carbon emissions over those 30 years or so. Another question I get asked quite a lot, which is, should we, for example, replace our gas boiler with a heat pump? And the answer is probably yes. There's the embodied carbon of a heat pump has to include all the infrastructure and bits and pieces you need to go with it, which in a poorly insulated house might include larger radiators, for example. Here we're taking a figure of 1,500 kilograms of carbon dioxide for that whole installation. That's open to debate. It could be higher, could be lower. The direct electric line here is assuming you've just got no heat pump, but electrically powered heating. And because the direct electric is starting at the origin of 0, 0 on that graph, that 1,500 I mentioned is really the differential between the heat pump installation and the direct electric installation, unless you've already got the direct electric installed. And it's going to depend a lot on your heat demand. The more energy used, the more sense it will have to have a heat pump. So there are two cases here. The left-hand one with 3,000 kilowatt hours a year, the right-hand one 6,000 kilowatt hours a year. And you see that even for the lower heat demand, you get quite a quick payback on the heat pump. It could be quicker than that if that initial embodied carbon estimate were lower. And of course, if there are a higher embodied carbon for the heat pump than assumed here, 1,500, and you've got a low heat demand, you might find yourself the orange line kind of catching up with the blue line a bit quicker, and maybe the heat pump can't be justified as much. But in most cases, there's a fairly good argument to say a heat pump will be a good idea for carbon considerations. The telling thing here really is the gas boiler. So almost regardless of the embodied carbon of the heat pump installation, you're going to catch up that gas boiler emissions pretty quickly. And that's an existing gas boiler. So carbon payback periods are not everything. We need to move to renewable energy generation. And this graph shows how important it is to consider the embodied carbon within renewables. This is a PV array, some options for different PV installations. And the difference here is the embodied carbon of the PV installation. Now, the embodied carbon of PV installation can vary quite widely. It does vary quite widely depending on the type and make. And it must include the whole installation, not just the panels, so the inverter and any optimizer you might have and various other bits and pieces. And there isn't really good information on this. A report by Elementary in February 2022 concentrated on the PV installation options with embodied carbon figures around 500 to 800 kilograms of carbon dioxide per kilowatt peak of the installation. And that included the panels and inverter and optimizer, etc. But it also highlighted some EPDs for PVs with embodied carbon closer to 1,600 kilograms of carbon dioxide per kilowatt peak. So the lines in this graph show that range. So the blue top one, about 400 kilograms of carbon dioxide per kilowatt peak of installation. The orange one, 800, and the lower grey one, 1,600. And you can see that the good ones are good, the medium ones are okay, and the high carbon ones are not okay. So really important when considering, what we think of as green technology, that we don't blow our embodied carbon budget on a system that's emitted too much carbon in its manufacture.
Toby, we just got a question in the chat,
Yeah.
which I think is pertinent to this. Is what's the sort of typical life expectancy of a PV array in your experience?
Well, I think manufacturers, we're happy to say at least 25 years, and this graph goes up to 25 years. But you see in 25 years' time, because the grid's hopefully mostly decarbonised in 25 years' time, those lines go very flat. So even if it lasted 50 years, it wouldn't change these results. That grey line isn't going to get to zero in 50 years, and those blue and orange lines aren't going to do much either.
That's great, thank you.
These graphs do take into account a decrement in performance each year in the panels. And these figures don't include batteries either. So batteries have a very, very, very poor data on their embodied carbon. In fact, if anyone has any good data, please do let me know. And in a domestic setting, you may never have carbon payback, given in the absence of battery storage, the excess energy produced by your PV array will go to grid and someone else will use it. So at worst, a battery can actually increase the carbon intensity of electricity by holding electricity generated at peak times, at peak grid times, for use at off-peak grid times. But if batteries were low carbon, i.e. low embodied carbon, or if you happen to have one anyway in the form of an electric vehicle battery, which is compatible with the grid, then they can be used to modulate grid demand, which means you can store energy produced at off-peak low carbon times and use it during peak times. But if what you're doing is using your battery to make sure you use all your PV, it's unlikely that's going to be a low carbon solution. Very briefly on wind, unlike photovoltaics, wind turbines are normally guaranteed to provide a very quick carbon payback period. These are a few studies. Some figures are quite old, from 2012 or so likely to be improved. But those kind of 5-10 grams of carbon dioxide per kilowatt hour are about as low as the grid will ever get. And the payback periods of less than a year is about as low as you could ever hope for. So just moving on quickly now, these graphs I'm showing you now are the answer to the question, if all I care about are the total atmospheric carbon emissions, should I make this particular improvement to operational efficiency that I've got in mind? And if you've got an operational improvement you want to make, you can choose a carbon payback period you want to achieve on the horizontal axis, the x-axis, and then read off the energy savings that improvement would have to make each year for each kilogram of carbon dioxide that improvement emitted in embodied carbon. So to try and explain that a bit more, say you want a 10-year carbon payback period, and you've got a heat pump. This is the left-hand graph. Then each kilogram of carbon dioxide that you emit into the atmosphere in making that operational improvements, say adding insulation or whatever it might be, has to deliver between 1.8 and 3.2 kilowatt hours per year of heat savings. And the differential depends on the grid decarbonisation curves that we've chosen. And the heat savings required if you do not have a heat pump are smaller by a factor of whatever the coefficient of performance of your heat pump is, so about 3 times smaller. And of course, it does assume that the decision to have a heat pump or not have a heat pump is made for some other reason. So we're not factoring the embodied carbon of the heat pump in these graphs. So I hope that's clearish.
Can you perhaps go through that one again? Because I know the first time you explained this to me, I was struggling because intuitively I'm thinking heat pump has to be better than direct electric heating because of the coefficient of power.
Yeah, it's because of a heat pump, you're getting 3 kilowatt hours of heat for every kilowatt hour of electricity you use. With a heat pump, the operational improvement you make, you're saving less electricity. You're saving about 3 times less electricity because your operational improvement is reducing your heat losses, and your heat losses and your electrical loss usage is 1/3 of your heat losses with a heat pump, whereas with direct electric heating, it's all of your heat loss. So that's why with a heat pump, the operational improvements have a lower impact on your operational carbon. And so, for example, and then the next slide maybe I'll clarify things a bit more. This wouldn't normally be used when you're thinking about how much insulation to put on, because those graphs I showed you earlier do that quite well. It's more about binary decisions. If we do this, will we get a payback in carbon terms? So, for example, in a super well insulated building, you might be looking to eradicate all the thermal bridges from your ground floor. And one common way to do that is to have a sub-base of foam glass of some kind and then cast a concrete slab over that. An alternative to that might be to have a suspended timber floor and accept your thermal bridges. And a suspended timber floor is almost always the lowest carbon ground floor typology. And the table here shows some typical embodied carbon figures for the different components of these floors. So for a concrete slab on a foam glass aggregate subbase, you go somewhere between 14 and 26 kilograms of carbon dioxide per square meter for the foam glass, plus another 25 for the concrete slab. So 40 to 50 kilograms of carbon dioxide per square meter. A suspended timber floor, and all these are normalized to the same R value. A suspended timber floor of the insulation needed for that R value has about 13 kilograms of carbon dioxide per square meter. So quite a big carbon saving in having an embodied carbon saving, having a suspended timber floor. And to run that through of numbers, if that differential were, say, 10 kilograms of carbon dioxide per square meter, and that's quite a conservative value looking at the table there, and you've got a 50 square meter footprint in your building, that's 500 kilograms of carbon dioxide extra for eliminating thermal bridges. And if you've got an air source heat pump and you're aiming for a carbon payback period of 10 years, then looking at a graph, the previous graph, somewhere between 1.8 and 3.2 kilowatt hours per square meter savings required. Let's call that 2.5. So we need to make savings of 2.5 kilowatt hours per year for each kilogram of carbon dioxide we spent. Now we spent 500 kilograms of carbon dioxide. So 500 times 2.5 is heat savings required of 1,250 kilowatt hours per year over that 50 square meter footprint, which is quite a lot. That equates to 25 kilowatt hours per year per square meter for the ground floor only, or if you've got a 2-story building, for the whole building, it'd be half that, 12.5 kilowatt hours per year per square meter. And if you're the kind of building where you're considering eradicating all thermal bridges, you're probably quite a low energy building. You might be around passive house, and passive house heat losses might be around 15 kilowatt hours. per year per square metre of your gross internal area. So the idea you'd make savings of 12.5 kilowatt hours per year per square metre of your gross internal area is unlikely from just eliminating those thermal bridges. But if we use these graphs from at the other end of the spectrum, we have an uninsulated stone wall where we're limited with the amount of insulation we can put on for other reasons like condensation on the inside. So we pretty couldn't take the U value much below about 0.3 anyway. So the question is, shall we insulate it in this way or not? And we run through the calculations there. And we find that with reference to the, we get a heat saving of about 3.4 kilowatt hours per year per kilogram of carbon dioxide emitted in making those improvements. And we look back at our graphs again, and we find we've got a payback period, depending on our heating solution, somewhere between 2 years and 9 years. Now, 2 years would be great. 9 years is quite a long time. And if we're at 9 years, we may start thinking about whether we could make that improvement in a lower carbon way. So just to wrap up, the really, really key thing, and I've seen this a lot recently, I see it regularly recently, is to not make operational carbon assessments without also considering the embodied carbon as well. You cannot do the two things in isolation. The atmosphere really doesn't distinguish between where the carbon dioxide has come from. And so I've seen schemes, optioneering for housing and buildings, insulation quantities, showing the performance of the buildings only. But it really can't be looked at in isolation like that. It has to include the embodied carbon assessment. And I can talk about the tram proposals in Edinburgh as well, which kind of do the same thing. And in fact, all other things being equal, the upfront embodied carbon may be considered more important than the operational carbon on a kilogram for kilogram basis, on the basis that a single release of carbon now, which is the upfront embodied carbon, has a greater climate impact than the same quantity of carbon dioxide released over many years. So releasing 50,000 tons of carbon dioxide in a single pulse now is worse for climate than releasing 500 kilograms of carbon dioxide per year for 100 years. And in a way, it's almost entirely analogous to a financial investment, in that you wouldn't spend £50,000 now to get a return of £500 for 100 years. The other reason that the upfront embodied carbon may be considered more important than operational carbon in the future is that the upfront emission is a far greater certainty of occurring. And when you factor in the probability to things, that becomes important. And also because the most critical climate crisis is hopefully now and not in 50 years' time. If we haven't made significant improvements in the next few decades, it's probably too late anyway. So on that cheerful note, I'll be very happy to have as many questions as possible in the time remaining.
Toby, can I just kick off with, I guess what might be an obvious question, of which I suspect there's not an easy answer, but you've certainly in my mind very clearly raised the fact that we need to think quite carefully about any interventions we make around operational carbon savings. And you've introduced some relatively complex graphs certainly to a layman or a generalist like me. Let's assume that the majority, if not all of us, leaving this webinar say, well, absolutely, I've learned something today and I'm going to think differently. Where might we go to start sort of accessing the sort of data that you've used and the sort of information, accepting that we're not going to become experts in, 5 minutes or even 5 years probably, but what might be a logical next step if we take on board what you've said and we want to start thinking carefully about it?
Yeah, so the key point here is that, as I hope was apparent, the decarbonisation of the grid is a real factor here, and these figures are published by the National Grid on a yearly basis. These are from 2022, a bit out of date. Like I said, they did release the 2023 ones, I guess, or 2024 ones this week. And if we don't factor in the decarbonisation of the grid when considering operational energy, we'll get very, very different results. So, and that will be inform closely what your operational emissions are doing over the next 30 years or so. And then, of course, the embodied carbon data comes from standard sources, whether whether you've got paid a one-click LCA subscription or whether you're looking up in the ICE database of embodied carbon, or directly to EPDs. EPDs are normally the best source. And I'd also say that all of these numbers have a wide range of error on them. I don't think any carbon calculation is accurate to within about half or double its true figure.
Okay.
So for example, when we look at graphs like this, actually, where you are in all these options, once you get below the 30 mm insulation, they're all pretty much the same carbon, really, in terms of the accuracy of the method.
Yeah, I guess the challenge, just looking at that graph you've got on there, is you can make what you're arguing is the optimum decision around carbon, but you won't get it through building regs, so therefore you can't do that. And so, that's, I guess, a question back to government, or how quickly our legislation can change to take account of this.
Yeah, and we may want to consider things beyond carbon as well, like, for example, heating bills. So it's a trick. I mean, really the question here, I think if you're in a position like this, the solution wouldn't be to insulate your building less. It'd be to insulate it with materials which have a lower embodied carbon, so you can have better insulation, which is why this graph shows you can have a U value way below anything you'd likely want in practice.
Yeah, yeah, which is a relatively sort of simple takeaway that we should look at, rather than just going out to the most readily available or the most widely used, which is absolutely not the lowest embodied carbon insulation. Maybe we need to do a bit more work to find the better solution.
And the building has to be designed from the outset so it can incorporate the low carbon materials, because you normally can't just swap out polystyrene with a natural material, which tend to be low carbon, because they're used in different ways.
Yeah. Excellent, thank you. Tobias had a question that he put in the chat earlier, which is more of a general question, I think, but to be fair to Tobias, if you'd like to come off mute and ask the question directly. It's assuming that Tobias is still there. Okay, let me read it out.
Doesn't have a mic, Simon.
Sorry?
Tobias doesn't have a mic.
Okay, thank you. Right, Tobias, I'll read your question out on your behalf then. So the question is, Toby, regarding the decarbonisation of the grid, the big question is, if you feel nuclear is technically decarbonisation or not, and also whether that's acceptable regarding risk and associated nuclear waste.
Well, as long as you factor in the embodied carbon of a nuclear power station into the operational emissions, which you should do, and that's what those wind turbine graphs were doing that I showed, then and if that's a low figure, which it won't be as low as wind, then it is decarbonisation. The nuclear waste is is not a carbon question, and I've been very keen to stress this whole talk has been about carbon only, and there are other reasons for doing things than just minimising carbon. And of course, nuclear waste is a biggie because it's not just nuclear waste, it's also the safety of the nuclear installations, which can be pretty disastrous if they go wrong, as we've seen in other countries. So personally, I'm not a big fan of nuclear. We'd need to work out how, if we were to rely more on it, we'd need to work out how to build nuclear power stations much quicker than we do. And I personally wouldn't suggest it's a good idea to let foreign states operate those installations.
Yeah, Tobias is adding that, which I think is an interesting point, particularly coming back to the carbon standpoint, that storage and decommissioning of nuclear plant is carbon intensive.
Yeah, that all has to be factored in, obviously, and so I know for sure it wouldn't be as low carbon as wind. Where it gets on the kind of grams per kilowatt hour over its lifetime, I don't know. But I don't see it as a long-term solution unless we solve some of those thorny issues around it, and I don't think we will do.
Yeah. Okay, those are all the questions in the chat. If we just have one more shout out, if anyone else has any additional questions, either drop it into the chat or please feel free to come off mute, assuming you have a microphone, and ask a question directly.
Oh, that's nice. It was so clear and
yeah. I think highly thought-provoking, to be honest, Toby. Particularly, I mean, even if we were just thinking about carbon, I think there's an awful lot to consider there and to take in. But as you've thrown up with the last slide, it's a complex activity. I think in reality, much as we all like to think there's a silver bullet out there, the reality is the complexity of the challenge is at least comparable with the complexity of the world that we live in today. So
yeah,
and
I showed lots of these graphs with very small differences between lots of lines on them, as if it can all be reduced to a mathematical formula, and it can't. At the end of the day, it will be a judgment call at some point about what you think the likelihood is, and what emphasis you place on which of these factors or parameters and other parameters I may have missed off it too.
Yeah, I think there's an interesting point there, which we probably won't get into now, but I know from my experience that I've done things that in hindsight actually weren't the best decision around carbon. But if I hadn't done them, I wouldn't have learned that, and therefore made the better decision the next time round. So again, that's adds a huge level of complexity. But
no, absolutely, and I'm learning a lot from my mistakes all the time, as most people are, and it'd just be nice if we could all learn from other people's mistakes too, so that we don't all make the same ones.
Indeed, which I think is a very nice point to sort of round off the presentation today. So thank you ever so much, Toby. I mean, you've covered a huge amount in 45 minutes with questions. I believe we'll have access to the slides within a day or two, so those can be shared. But yeah, thank you very much for sharing that information, and I suspect you might have one or two inquiries coming your way when people digest the content of today. So thank you.
Yep, no, thank you to everyone for listening, and yeah, great.